Okay, so we were doing quasi-periodic motion last time. And just to recap, uh, n-dimensional or n-frequency quasi-periodic motion can be viewed or considered as a trajectory on an n-dimensional torus. So when n was 2, we saw the conditions for quasi-periodicity was that the frequency has to be, the ratio of the frequencies has to be an irrational number, and that's how the trajectory keeps on wrapping around the torus without closing. No closed orbits, no periodicity, and the trajectory is such that after a long time it's going to fill the torus. That means it's going to come arbitrarily close to each point on the torus. We also saw what happens when the ratio of the frequencies. Now, in the last lecture I said this is a larger frequency. It need not be. The ratio of the frequencies across this path and across this path, what happens when it's a rational number? Well, when it's a rational number, then you'll get eventually the orbits are going to wrap around and close. So you will have closed orbits, periodic motion. So we are continuing this. This is 11. So in general, if I have a rational number p by q, which is the ratio of the frequencies, the frequencies are inversely related to the time period. So the period around the torus is given by pt1 equals to qt2, where T1 and T2 were the periods corresponding to omega 1 and omega 2 respectively. This was, let's say, omega 1 and motion cross, this was omega 2. In fact, one gets very interesting shapes if you look at it. So if omega 1 by omega 2 is 3 by 2, you can see you will get something called as a trefoil knot, which is essentially around the torus, and so it goes around, it goes around, goes around, and it goes around. You are going to get a trefoil knot, which essentially means is that once you cover an entire rotation on the one of the orbits, you will be covering 2/3 of the motion across the other circle. So that's called the trefoil knot. And in general, you're going to get very interesting knots on the torus, depending upon the winding number or the rotation number. You get very interesting knots. The way this motion or the trajectory wraps around the torus, depending upon omega 1 and omega 2. Remember, when omega 1 divided by omega 2 is an irrational number, you don't get any knot. That is, the trajectory doesn't close on itself, it's going to wrap around the circle. So that was, we talked about quasiperiodicity. With this, we come to the next topic, which is coupled oscillators. Now, we've already in some sense seen what happens to individual oscillators. Let's say I have theta dot equals to omega 1 and theta 2 dot equals to omega 2. So this basically represents two oscillators. Why I'm calling this oscillator? Because this can be regarded as a map on a circle where I have theta 1 and this is another trajectory, theta 2, and I can regard this motion on a circle with an angular velocity omega 1. Now notice, this is not the frequency, but this can be regarded as an angular velocity. Omega 2 is the speed on the circle. So these are two oscillators, and this map means that essentially they are independent of each other. They are like two independent runners on a track. But there can be a coupling between them. So for example, they can be something like that. And for example, let's take a specific example of that. This is a model of coupled oscillators. Where I can say theta 1 and theta 2 are the phases of the oscillators. And one can regard omega 1, omega 2 as natural frequency of the oscillators, and K1 and K2 are the coupling constants. Now, such a model can be represented as two friends jogging on a circular track, and there is some coupling between them. They want to jog together. Essentially, that's what. If K1 and K2 are 0, then they are just two people who are not friends. They are jogging on a circular track, one with theta 1, and on the same track, the other guy can be theta 2 with omega 1 and omega 2, essentially. So one can analyze this as in two ways. We can realize this as a motion on two circles at these rates, or one can also alternatively, one could imagine a single point tracing out a trajectory on a torus with coordinates theta 1 and theta 2. This is theta 1. This is theta 2. So this motion can be represented as a trajectory on a torus with coordinates theta 1 and theta 2. And essentially our entire formalism follows from our previous example. So for example, when K1 and K2 are 0, you just has theta 1 equals to omega 1 and theta 2 equals to omega 2, and depending upon omega 1 divided by omega 2 is a rational number, rational or irrational number. I'll have closed periodic orbits, or I'll have quasi-periodicity. Well, what happens when, so this is the case when K1 equals to K2 equals to 0. What happens when I have K1 and K2 not 0? Then I have a system of coupled oscillators, essentially. And it's convenient to looking at the phase difference, phi equals to theta 1 minus theta 2 as a new coordinate, and under the new coordinate my equation becomes phi dot equals to theta 1 dot minus theta 2 dot equals to omega 1 minus omega 2 minus K1 plus K2 sine phi. Now, depending upon the values of the magnitude of this quantity compared to this quantity, omega 1 minus omega 2 modulus, if this is less than K1 plus K2, well then, what do you expect? I'll get fixed points of this math. Remember how I get the fixed points? I'll put phi dot equals to 0 and I'll see what are the conditions. So for phi dot equals to 0, for the points to be 6, the conditions is for the fixed point, my sine phi should be equals to omega 1 minus omega 2 divided by K1 plus K2. Of course, when K1 plus K2 is less than omega 1 minus omega 2, then, well, I have imaginary fixed points. So these are the value of phi star at which I get two fixed points, and you can see this equation would be satisfied by 2 points. phi 1, phi 2, each of them yielding sine phi equals to omega 1 minus omega 2 by k1 plus k2. And you can analyze what are the stable fixed points. So if I draw a phase space diagram of phi dot and phi, I'll get one stable fixed point, so just to recap, we started with the equations for the two oscillators, and from that we got a equation in terms of the variable phi dot, and we demanded phi dot equals to 0 to analyze the fixed point. Now what does phi dot equals to 0 means? That means theta 1 dot equals to essentially theta 2 dot, or that is when the oscillators are going in a phase locked manner, in the sense that the phase difference between the oscillators is going to be constant. So this is a phase locked solution and the oscillators are separated by constant phase difference given by phi star, which was given by sine phi star equals to omega 1 minus omega 2 by k1 plus k2. And the oscillators go at a constant frequency. Both the oscillators go at a constant frequency, which is given by omega star, which can be shown to be omega 2 plus k sine phi star, or this is the compromised frequency. Why is this called the compromised frequency? Because it lies between the natural frequencies of the two oscillators. Two oscillators. So, in short, when we have a coupling, then depending upon the parameters k1, k2, omega 1, omega 2, we can have the coupled oscillator system, both of the oscillators going at a constant compromised frequency, and also with a constant phase difference given by this angle. Thank you.